So hello, I'm Kris, and in this session I will I'll take you through an experiment I did and hopefully make the case that online development, including the full cycle of software engineering with microcontrollers, is actually possible. And furthermore, that is possible with modern C++, C++20, and also that with having that in mind, that we'll get even better performance by leveraging C++20 and modern C++ than hundreds and C-like solutions. So if that sounds compelling to you, stay tuned, and without further ado, let's dig in and see how we'll go about it. So what's the agenda for today? At first, we'll just I give you a bit of motivation already, but we'll also establish a goal and how we'll go about it in this talk. We'll explore some tools and libraries, online libraries and online tools, because in this day and age, everything is about web, and I think like embedded stuff is not really leveraged yet in that space. So I think it'll be really exciting to see how we can do it. And in order to do so, we'll do a simple project, which will be a switcher based on microcontroller, obviously. We'll do the full cycle, including the design, implementation, testing, and simulation online. So that will be the exciting part. I'm looking forward to sharing, that with you. Hopefully, we'll do a small demo of the online tools, and we'll see how that works, and we'll sum it up. Just a reminder that if there will be some code just to show off the modern C++. So if you have any dark blue background on the slides, that will be something to remember and something important. So yeah, let's go and begin. So the motivation. Obviously, we have microcontrollers available. You can buy them. But what if you actually don't have it and you would like to start? So you can imagine the use case that, I'm just a developer. I would like to try a hobby, or I just want to get into Arduino or ArcMegas or whatever. But I don't have it yet. I don't know how to start with it. Everything seems to be complicated in embedded world, and what to do? Well, there's not much we can do at the moment. Well, we can, but not out of the box. So there is like Arduino IDE. However, it supports only GCC 7.3 and C++11 out of the box. So if you don't do it yourself and change the flags, you may not be able to leverage the most modern C++, which is a bummer. What about simulation online? That's hard to potentially do as well. If you don't have a microcontroller, or if you don't have proper tools installed, might be difficult to start. And this talk is about how can I easily start? I have nothing. I just want to go about it and do it right. What about modern C++? If you take a look online, you'll find all these C-style-like courses with Arduino, where you have global variables and tons of if statements, blah, blah, blah. Not the best code, C-style, not also the most performant ones as well, which I will try to prove here. So all of that is not really encouraging, at least to me, and I think we can do better. And I hope to show that in this talk. So what's the goal? The goal is to implement a simple project, a switcher, which will have a button and an LED, which we will try to switch. Fully online, the whole cycle, as I pointed out before, with C++20 and for multiple architectures. So it will be for Arduino and for the microcontroller, which is the cheaper version of it as well, which is compatible with that library. What kind of tools we'll use? So for the design, there will be plant UML. We'll design our state machine because we'll use the state machine for that. for the talk, so that we'll avoid all this branching and global variables and stuff. So there'll be planned UML for that. Implementation, we'll use and leverage one of the best tools available to experiment online, Compiler Explorer. We'll try to use modern C++. Compiler Explorer supports GCC 9.2 with C++20. It also supports GCC Trang and Clang Trang, which we'll leverage for testing, because we can do a lot of things with Compiler Explorer. We'll leverage some libraries, and we'll do them by including the HTTP, which is a unique feature for Compiler Explorer, but it lets us easily experiment with heterogeneous libraries. We'll also do the cross-compilation. So we'll do the same code. We'll compile the same code for two different architectures, and also we'll compile and run the tests all in one instance of Compiler Explorer, which is super powerful. And because we can test it immediately, we can do TDD and see the results of our tests, and also the assembly output for our microcontrollers. Testing, we'll leverage the UT framework, which I'm the author of. It's C++20, but that's fine because we can do it inside the Compiler Explorer. We can combine different versions of C++. It's a single header module, not a big one, 2000 line of code. Only requires STL, but that's not really important. It's macro-free, so that's why I wanted to use it, because I wanted to present the modern C++. What about implementation? As I pointed out, we'll try to leverage state machines instead of trying to go with the naive C-style-like approach with if-else switch statements and stuff like that, for the performance reasons and for easy to explain flow reasons as well. And also we'll, I have also the versions with the switch and if, but we'll just compare them. So it's C++ 14. It's UML 2.5 compliant, which is important if you follow the state machine diagrams. It's single header, so we can include in the Godbolt. Nothing is required for it, so neither boost nor STL. So it's perfect for embedded stuff, because we can just include that file, get it online, and just go about it. It's supported without any virtuals, RTTI, no exceptions required. It's just perfect for embedded stuff as well. And it has really a lot of policies to get performance out of it, and it will be faster than hundreds of solutions in the end. For simulation, we'll use a website called Tinkercad, which allows to leverage some of the microcontrollers available. So there's Arduino, for example, on it, which we can experiment with. There are others as well, and there are quite a few components to start with. So okay, let's dig into the project. As I pointed out, the project will be a switcher. So if we write the requirements for it, the feature will be to turn on and off the LED when the button is switched. So we will have two scenarios which we'll try to implement. Assuming that we have a board which has a button and LED. When we switch the button, and when the button is like switch off and the LED is off, when we switch the button, we'll turn on the LED. Obviously, that's a very simple use case. And the other scenario would be the vice versa for that use case. So we'll get switching via turning on the LED via switching the button. I hope that makes sense, and I hope we can move on. So design, as I pointed out, we'll use PlantUML to design it. PlantUML is an online tool which will allow us to write code like that, which is a state machine text-based UML diagram, and that will generate a code like that. So that will be the design. We'll start in the off state when the button will be pressed and the button is on, meaning is the high. In the high state, we will just turn on the LED and we'll get to the on state. And after that, when we press the button again and it will be in the low state, meaning that we switch it off, then we will turn off the LED. So when we will have the demo, I will show the tool itself, but you can see how easy it is to start the design. You can start from very simple text and get the really nice picture out of it to share with your coworkers or share the design. So implementation will be in C++20. So we'll start from concepts, which are C++20 addition. So we'll start with the concept component, and we'll have 3 requirements for it. It will be a setup, on and off. Setup will just set the pin mode, and on and off will just verify whether when we read from the pin, what kind of state it is in. And then we'll have abstractions, because we'll use C++. So we want to leverage zero overhead abstractions, and one of them will be an LED implementation of that concept. For the setup, we'll just set the pin mode, and pin mode is Arduino implementation from the library of Arduino. And we'll set it to output, obviously, because it's an LED, and on and off will just read whether the state of the pin. Button will be very similar. We'll set the pin mode as an input. On and off will depend on the pressed function, which will read from the pin, and if the state is high, the button is switched, and when the state is low, the button state will be off, and it means that the button gonna switch off. So I hope that makes sense. We have really nice 2 abstractions with the component as well. So moving on. Okay, well, just a reminder that concepts are something which is added in C++20. The type constraints, they act like a documentation for interfaces, and they mainly provide the better error messages because they are done on the point of instantiation on the callee side, not the library side. So you won't get the error messages from the STL or from within the library, which is important. They also gives you faster compilation times if you do a lot of spinner enable if. So they're great. They come in, and let's leverage them when we can. So let's dig into the implementation a bit more. As I pointed out, it's based on the state machine. So that's our state machine design. If you look at it from kind of a raw perspective, you can translate this diagram to 2 rows, basically. One is that we start from the off state. In the off state, when we press the when the button is pressed and the guard is on, then we turn on the LED. And if you in the on state, when the button is pressed and it's in the low state, we turn off the LED. I hope that makes sense. And that's the implementation of using the SML library in C++. So if you didn't realize, the UML has a specific syntax for the state machine transition, and you can find it on the transition DSL on the bottom code. It starts from the source state. After this, there is an event. In the square brackets, you have a guard, and followed by the / there is an action and a destination state. So if the guard is satisfied, so if you're in the source state and the event is received, and the guard associated with that event is satisfied, then the action will happen after the /, and after that the state will be changed to destination state. So that's the way of expressing the flow using the UML state diagrams. And you can see on the bottom that the C++ implementation using SML library is very similar to the one on the top, which is great because we can leverage the same kind of approach towards both. You can see that the star is the initial state. After that, you have off state, event, guard, and action. So I hope that makes sense because I'm going quite quick. But the point is here that it's super easy to implement state machines. And instead of having global variables which you try to follow everywhere, you can just have the flow in the state machine instead. So what about the abstraction for the application itself? We'll have the switcher, which will take the button and the LED component. Instead of type name, or a class, we can put the concepts here. After that, we'll have the switcher constructor, which will just do this nifty trick from C++20, which is called immediately invoked lambda expressions with the familiar syntax, where you can, get this button and LED in the TSs in a sense, and after they just call setup on all of them. So that will basically do the same as button, : setup, LED, : setup. You can imagine that if you have more components, that might be beneficial. And after that, we'll have just the call operator, which will implement the transition table, which we expressed before. So that's it. That's our application. There's not much about it. There's something to remember. It's that C++20 gives us this nice way of immediately invoked function expressions to deal with, and it's a really nice pattern. If you haven't followed that one, I would encourage you to do so because it gives a lot of leverage to do really cool stuff with TMP. So testing, I think it's important to do the testing, obviously, and to do the testing with BDD or TDD fashion. So wherever you do that, we can do that with the UT framework and test the state machine. It's really hard to test the global state if you have global variables and a lot of if statements, but it's really easy to test state machines. And here we have just a button and LED. We create the state machine with the switcher. That are just fake ones. And after that, we should start in the off state. So we just verify that the state machine is in the off state by default. And then we can just process event, which is the pressed event, and see that it will just change the state to on and off depending when we switch it accordingly. So that's very easy to test, and that's pretty cool to start with. But what about the main implementation? So that will be the second main. We'll have two mains. One is for testing, one is for the release code. We'll have the switcher, and here we'll have different implementations for different microcontrollers. For the Arduino, we'll just use button 2 and LED 11, which are the names for the outputs and inputs, which we'll leverage in the demo. For the other one, we'll just use PB1 or PB0, depending on our board, so we can easily change that. And after that, we have the main loop with the for. That will just go forever. And we'll leverage the same trig as before and process all the events which will come from the state machine. State machine has this cool feature to avoid boilerplate code to give us all the events which are required, and we'll just get them processed by just calling and process event on the state machine. So we'll get all the events and we call process event on them and verify the guards, whether they on or off. So that's pretty cool. Not a lot of code, just to move on. And you see that the design makes it really easy to extend. Maybe it's an overkill for this very simple example, but in the long term, when you have a lot of components, you can see how beneficial that would be, because this 4 here will never change. You'll just add more components, which are zero overhead abstractions either way. So what about the performance of it? Because that's kind of important in the embedded world, and we want to have small code size, and we want to have fast performance. So I implemented it using the kind of Arduino approach, when you have the loop, global state, and setup. And you can see you get 44 lines of assembly. I'm not claiming that assembly is the lower number of code. Assembly is always better, because that depends on the instructions. But in that case, when we have very similar instructions, it's actually the case. So you can see that we compile for a compiler, a specific compiler here, specific architecture, and we get 44 lines of code. If we do it just in main with if-else statements, we get a bit better, because we don't have the global state anymore, which had to be shared between the loop and the setup. When everything is inlined in one function, we get a bit better code, better optimized code with 32 lines, but still quite a lot in comparison to the SML and C++20 version, where we get 24 lines of code. So that's the winner. And you see that C++20, by leveraging SML library and zero overhead abstractions and all these C++ TMP magic here, which potentially can give us better scalability and maintainability in the future, because we don't have to repeat ourselves a lot of time, actually gives us the most performant code as well, just 24 lines of code. So that's pretty cool. That's exciting. So just to sum up, with C++11 or C style, like if-else globals, you can say it's just C basically, 44, 32 lines, and with C++20 state machine approach, 24 lines of code of produce assembly. And if you don't believe me, you can try it on Godbolt yourself. There is a link provided. So what about the simulation? In order to put that on the Tinkercad, we'll just do the empty setup, and in the loop, because Tinkercad supports only Arduinos, we'll just use assembly and just put the assembly output from the compiler explorer into it. So that's a nifty trick which we can leverage to not to deal with the external libraries and other stuff in the Tinkercad. So that will look like. So that's our board for Arduino. We have an LED, on the board. We have the switcher as well, and after that we just copy paste the output from the Godbolt into the Arduino Tinkercad, and we'll just run it. And the same for other microcontrollers as well. And we'll have to have a different assembly output because of the different instructions, but basically that's it. So we have a few minutes, so let's just try to do the demo. So what about the design? As I pointed out, you can try it online. You'll get the image. If you go back, and we'll go to the implementation. That's the part which is the most exciting. That's the full implementation of it. We'll have the two versions. One when the microcontroller is defined, otherwise if it's not. So that's the implementation which I gone through already. That's the testing as well. So you can see all the tests are passing. They can be run as well here. And that's the produced output for the Arduino, and that's for the other one as well. You get 24 lines of code, but a bit different instructions as well, because this one is using rcall and this one is using call, whatever. Doesn't really matter. But the idea is that you copy that code into the Tinkercad implementation of the board, and you can simulate it and test it as well. So here you can test the code itself, and that's all the test, which can be run in the Godbolt. Here you have the produced assembly for one architecture. Here is for the second one, And that's the whole implementation of it. And here you can see the includes for the libraries. And if you go to simulation, you see that you can share it as well, like in Godbolt, so that's pretty cool. We can click simulate as well. You'll see the code. It's copied from the Godbolt. You can tinker that and change it as well, which is super cool. We can start the simulation, and when we do the switch, and we'll just turn on off the LED, fully online. You can share it with your mates as well, which is pretty cool. We can also check it for the cheaper version of Arduino as well, which is less than $1. You see the code, copy it from the Godbolt, start the simulation, and it also works. So that's pretty cool. And that's basically it. So as you can see, just to sum up, I believe that online development with microcontrollers is possible, especially it is possible with C++20. With tools like PlantUML, Compiler Explorer, and Tinkercad, we explored that. You can leverage online tools and start if you don't have anything. Just see, use, and see how it works. Experiment, leverage the modern C++, modern libraries, gain the performance whilst doing that as well. So that's even for the advanced users, something to remember as well. As I pointed out, you can leverage the libraries, get really expressive, get well optimized, better than the if-else or switch cases as well. And C++20 has a lot of, and C++ itself has a lot of abstractions, zero overhead, and libraries which can be used to get the most out of it and enjoy the development of it. So just to sum up, I think the mission statement here is like just let's embed all the things with C++20 and let's do it online. If you cannot afford microcontrollers, or if you don't want to screw them but you want to verify how they work quickly and see whether it's for you or whether you love it, just do it online and just go for it. Slides are provided. You can click of them if you want to verify them. And if you're interested in SML or UT libraries, you can check them on GitHub as well. So with that, I guess that's it, and I'm open for questions.